Welcome. Today we're going to explore the function f of x equals natural log of x times e to the x. Let's break down this interesting function, understand its properties, and learn how to differentiate it. Let's first understand what's inside the natural log. We have x multiplied by e to the x. This means our input must be positive for the natural log to be defined, since we can't take the natural log of a negative number or zero. Let's determine the domain. For the natural log to exist, we need x e to the x to be greater than 0. When x is positive, e to the x is always positive, so their product is positive. When x is negative, e to the x is still positive, but x is negative, so we need to check when their product is positive. Let's visualize the function x e to the x first. Here's its graph. Notice that it crosses the x-axis at x equals 0 and approaches positive infinity as x approaches either positive or negative infinity. Therefore, the domain of our function ln of x e to the x is all real numbers except 0, since x e to the x is positive everywhere except at x equals 0. Now, let's look at the graph of our full function, ln of x e to the x. Notice how taking the natural log transforms the shape. The function approaches negative infinity as x approaches 0 from either direction. Let's differentiate this function. We'll use the chain rule since we have a composition of functions. The derivative of ln of u with respect to u is 1 over u, and we multiply this by the derivative of the inner function. So the derivative is 1 over x e to the x times the derivative of x e to the x. Using the product rule, the derivative of x e to the x is e to the x plus x e to the x. Therefore, our final derivative is 1 plus 1. Let's solve an example problem. Find the value of the derivative of ln of x e to the x at x equals 1. We just found that the derivative is always equal to 2, so at x equals 1, the derivative equals 2. In conclusion, we've explored the function ln of x e to the x, found its domain, visualized its graph, and derived its surprisingly simple derivative. This is a great example of how combining elementary functions can lead to interesting results.